Hi everybody, I'm Giulia Bartolotti. I'm from the DET, the Electronic Department, and today I will present you my project that is a design project in the field of integrated Doherty Power Amplifiers in order to achieve wideband real case scenario of power amplifiers in the field of small cell for 5G base stations. So first I will present you some research background and the motivation of this project, then the design and the layout that led to the fabrication of a circuit that we experimentally characterized, and then I will show you the results and the role of this design inside the work of the research group. So I'm part of a group that works on microelectronics and power amplifiers. So power amplifiers, as you can see, are the last stage of the current communication systems, and therefore they are crucial and they impact a lot the overall performance. So the basic target for this kind of circuit are power and efficiency, but the group is also focusing on extending these designs to include the linearity, to improve the linearity performance, and to maintain this performance in case of load variations. Also, we try to extend it to multi-stage designs and in the field of integrated circuits. First of all, the circuit that we design is a Doherty, and Doherty is a well-known topology in this field because you can see the topology on the left. It foresees two power amplifiers. The second one, the auxiliary, injects some current in the load seen by the first one, the main, and therefore it changes the load that the main sees. By doing that, this process is called load modulation, we can achieve high efficiency also in the COF, so for power lower than the maximum one. This is important because current communication schemes works on average at a lower output power than the maximum. So we want our communication schemes to be efficient, and therefore we need high efficiency in the COF, and we use Doherty for that. The motivation for these specific Doherty designs are that we want to achieve real case scenario performance. Real case means that the gain cannot be just a simple power amplifier single stage. The linear gain needs to be higher than 15 dBs. Moreover, in the application of base station, we use integrated power amplifier, integrated technology, and for 5G base station small cell type, we chose as a target 5 watts. Moreover, the second biggest target for this design was a wideband, to achieve a wideband. This is important to achieve high data rates in communication schemes, and also to allow some interoperability among all the standards that we currently use. So wideband and the real case scenario gain and power, that's what we wanted, alongside with other usual requirements for this kind of circuit, that is a certain amount of oboe, and for an integrated circuit is a constrained chip size. How did we achieve that? To achieve the gain, we introduced two stages. So we introduced one driver for each power amplifier. In order to achieve the power, we selected the gallium nitride technology, and you can see on the bottom right how the resulting topology is much simpler compared to other ones. This simplicity also helped us to achieve a wideband design. The other strategy in order to achieve a wideband design was also to implement a specific combiner, to use a specific combiner from the literature. The combiner is really a crucial part to achieve widebands because it has some quarter wavelength transform whose behavior is frequency dependent, and these are needed, cannot take out of the design. So we recurred, as I was telling you, to the solution from the literature. This solution for an ultra-wideband Doherty was first applied in the case of hybrid circuits, and also to a single-stage topology. So this was the first time to apply it to an integrated circuit and to a two-stage topology. Also the parasitic were included. On the bottom right, you can see how we effectively manage to achieve a load modulation, so a change in the load seen by the main for all the frequency in our band. This is the final layout we landed on. In order to remain inside the constraint of the size, we used a lump topology, lumped components for capacitors and inductors, and we reduced the number of these components in the matching networks as much as possible. This compactness was also involved also the most bulky components, like the input power splitter. You can see many bands, and in order to ensure these components' performance in the case of these bands, we also perform a heavy EM simulation by the end of the design. So at the end, we effectively managed to remain inside the chip sizes of 3.7 per 3.3 millimeters squared. Now I will show you the experimental characterization of the fabricated circuit. So we perform some characterization first in low power condition, that for high power with power widths for many frequency in our band. Here in the graph I also showing you the linearity characterization of the circuit performed with a vector network analyzer by Keysight. And by the blue curve, with respect to the red one, we can see that the circuit can be effectively linearized. We were using a digital predistortion model provided with the Keysight instrument, and we obtain as a final result an error vector magnitude of about 1.5%, which is good. A good value are considered below 5, and so this proves that this circuit can also be linearized through digital predistortion. Here I am presenting you the final result in large signal. So first of all, I want you to notice that the dashed curves and the continuous curves, so the measured and the simulated results are pretty close. This means that the process was quite reliable, and we were able to achieve the expected result. And second of all, you can see, comparing the blue curve and the red curve, that the efficiency, the power added efficiency at saturation and at 6 dB of power back-off were almost same and above 20. So this feature of Doherty Power Amplifier of enhanced efficiency in back-off was also achieved. To resume, the small signal gain was higher than 19 dB. We achieved this performance over the whole 41% bandwidth, and the power was the targeted one of 5 watts, and the PAE was higher than 20 watts both at saturation and in oboe. Here I want to show you some comparison with the state-of-the-art designs. So I want you to notice that even if our performance are not the best in each of the specifications, there is no actual circuit that is able to do that. So the first and second row are single-stage amplifiers. That means that they are low gain, not really suitable for real case scenario. So these first two circuits achieved really wide bands, even higher than ours, which was already wide, but with a lower gain. And also one of them was hybrid circuit, so its losses were less compared to our implementation. In the third row, I show you a two-stage topology, so something that can be good and applicable to real case scenario performance, but you can see that the bandwidth was much lower than ours. And on the final stage, you can see a pretty good design that is able to achieve all the performance, all the target specification, but it is a gallium arsenide, so a different process, but the target power is much lower, so it's kind of a different circuit compared to our case. So overall, we can say that our performance were pretty good in terms of bandwidth, power, and gain. What we were not really satisfied with was the power added efficiency, that a 5 dB over was higher than 25%. You can see lower than others. So, as I was telling you, and on the right you can see a photo in a microscope of the realized circuit. That we achieve our target specification. One further future development is to, for sure, improve the efficiency. We did that already at simulation level with a slightly different process but with the same topology, and so we can also say that this topology can actually reach higher power added efficiency performance. So now, what is the role of the circuit in the wider scope of the research group? First of all, we already checked the linearity of the circuit, and we think that the really simple topology of the circuit can be good to apply some linearity improvement strategies, because they rely on the load, the input of the output of the device, and the fact that we just have two-power device plus the driver can be good compared to the really complex situation in other situation. Second of all, we checked the performance in a case of load variation. You can see the red curve of our circuit, the performance in terms of efficiency were varying a lot. What we can do is use the design circuit as the main cell to build a balanced topology that has proved to improve the load variation performance. And you can see by the blue curve that already using our circuit as main cell, the variations of the performance can be reduced a lot. So this is what I wanted to tell you about the wider scope of our research. And thank you for your attention.